Welcome back. Let's look at some examples involving direction cosines. All right, so here's our first example. We want to find the direction cosines and angles for vector v, which is the position vector of the point 1, 2, 2, and we want to show that the sum of the squares of the direction cosines is 1. All right, we'll worry about this last part later. For now, let's just focus on the first part of this problem, which is to find the direction cosines and angles for this vector. All right, and so if we want to find the direction cosines for this vector, we need to know the following formulas. There are three different direction cosines for a given vector. In particular, we have cosine alpha, cosine beta, and cosine gamma. Each of those letters, alpha, beta, and gamma, represent an angle that our vector makes with one of the three axes of the three-dimensional coordinate system. Alpha represents the angle that our vector makes with the positive x-axis. Beta represents the angle that our vector makes with the positive y-axis. And gamma represents the angle that our vector makes with the positive z-axis. All right, and so to find each of these direction cosines, what we need to do is take the corresponding component from our vector and then divide it by the magnitude of that vector. All right, so cosine alpha is equal to v1 divided by the magnitude of vector v, where v1 is the x component of vector v. Cosine of beta is equal to v2 divided by the magnitude of vector v, where v2 is the y component of our vector, and cosine of gamma is equal to v3 divided by the magnitude of vector v, where v3 is the z component of our vector. And so just to make it easier for us to reference, we know that v1, the x component, is 1, v2 is the y component, which is equal to 2, and v3 is the z component, which is also equal to 2. All right, that comes from our vector right here. Now, the other thing that we need to know in order to calculate these direction cosines is the magnitude of our vector. And so let's find that right now. The magnitude of vector v will be equal to the square root of the sum of its components squared. So we'll have 1 squared plus 2 squared plus 2 squared, right? We took each of those components, squared them, and we're adding them together. 1 squared is 1 and 2 squared is 4. So this is equal to the square root of 1 plus 4 plus 4. And 1 plus 4 is 5 plus 4 is 9. So this is equal to the square root of 9, which is equal to 3. All right, so the magnitude of vector v is 3. So we can use that value when we calculate each of our direction cosines. In fact, we are now ready to do that because we have everything that we need. We have v1, v2, and v3. And now we also have the magnitude of vector v, which is 3. All right, so let's start with cosine of alpha. Cosine of alpha will be equal to v1 divided by the magnitude of vector v. So we'll have 1 divided by 3, or in other words, we'll have 1/3. Then we'll find cosine beta. That will be equal to v2 divided by the magnitude of vector v. So we'll have 2 divided by 3, or 2/3. And then cosine of gamma will be equal to v3 divided by the magnitude of vector v, and v3 is equal to 2, so we'll have 2 divided by 3 again, which is 2/3. All right, so now we've completed the first part of this problem. We have found the direction cosines for this vector, but we also want to find our direction angles, and that would be alpha, beta, and gamma. So all we have to do to solve for those angles is use the inverse cosine function, or the arc cosine function, however you like to refer to it. And so if we do that for these three equations here, we're going to be solving for alpha, beta, and gamma. Those are our three direction angles. Alpha will be equal to the inverse cosine function, or arc cosine, of 1/3. Beta will be equal to arc cosine of 2/3. And gamma will be equal to arc cosine of 2/3 as well. All right, so now all we have to do to find alpha, beta, and gamma is plug these expressions into a calculator. And so if we do that, we will find that alpha is equal to 1.23 radians, and that's rounded off. There are more decimal places than that. I just decided to round off my radian values to 2 decimal places. And then if you like to work in degrees, alpha would be equal to 70.5 degrees. All right, so these are both the same angle. It's just that one is in radians and the other is in degrees. So that's alpha. That's what you get if you plug arc cosine of 1/3 into your calculator. Now let's solve for beta. If you plug arc cosine of 2/3 into your calculator, you will find that beta is equal to 0.84 radians. Once again, that is a rounded value. And I think I forgot to mention this, but this degrees value is also rounded off. There are some more decimals there. I just decided to round off to 1 decimal place for the degrees. But then if we convert this angle in radians into degrees, angle beta will be equal to 48.2 degrees. And that would be angle beta. And once again, that angle is also rounded off. All right, so that's angle beta. And angle gamma is actually going to be the same thing because we have arc cosine of 2/3 again. So angle beta and angle gamma are the exact same angle. All right, so angle gamma is equal to 0.84 radians, or if you like to work in degrees, that is 48.2 degrees. All right, and so those are our direction angles. These 3 angles represent the direction of vector v in the 3-dimensional coordinate system. But we're not quite done yet with this example. There's one more thing we need to do, which is to show that the sum of the squares of the direction cosines is 1. And essentially what that means is this. We need to show that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. That is what that means. The sum of the squares of the direction cosines is 1. We have each of our direction cosines squared, we're summing them together, and they must be equal to 1. So let's see if that's true. We have our 3 direction cosines right here. Cosine alpha is 1/3, cosine beta is 2/3, and cosine gamma is also 2/3. And so if we plug those values into this equation, let's see if it holds true, we will have 1/3 squared plus 2/3 squared plus 2/3 squared. All right, and we want to see if that's equal to 1. And so if we square each of these fractions, 1/3 squared is 1/9. So I'm going to erase this and write 1/9. 2/3 squared will be 4 divided by 9, or 4/9. So we will have 4/9. And then we have 2/3 squared again, which is also 4/9. All right, and so we have 1/9 plus 4/9 plus 4/9. All 3 of those fractions have the same denominator of 9, so we can add the numerators. And 1 plus 4 is 5, plus 4 is 9, so we have 9/9, which is just equal to 1. And so this checks out. We can now conclude that the sum of the squares of the direction cosines is 1. And if you have the right direction cosines, that will always be true for any vector. All right, the sum of the squares of those direction cosines will always be equal to 1. Okay, and so we showed that that was true for this vector. And so with that, that's it for this example, but let's take a look at another example where we find the direction cosines and angles for a different vector. Okay, so here's our second example. We want to find the direction cosines and angles for vector w, which is equal to 6j minus 4k, and we want to show once again that the sum of the squares of the direction cosines is 1. All right, so let's start off by finding the direction cosines and angles for this vector. This time I'm not going to have the formulas down here for us to reference. It's going to be good for you to try to memorize those formulas for the direction cosines. If that seems intimidating, don't worry. I'm going to show you here that it's not as bad as it may seem. First of all, let's rewrite this vector into the standard form so it's more clear what each of our components are. Vector w would also be equal to this vector of 0, 6, -4, right? We just took the coefficients of I, j, and k from this vector. There is no I term, so the coefficient of I must be 0, so our x component is 0. The coefficient of j is 6, so the y component is 6, and the coefficient of k is -4, so the z component is -4. All right, so this is the vector that we're working with. This is vector w, and if we want to find the direction cosines, we're going to need a couple things. We want to explicitly identify each of our components, and then we're also going to need the magnitude of vector w, right? Because here's what our direction cosine formulas are going to look like for this vector. Remember that there are three of them, one for each angle that our vector makes with the three different axes of the 3D coordinate system. We'll have cosine of alpha, which represents the angle that our vector makes with the positive x-axis. That will be equal to the x component of our vector divided by the magnitude of that vector. All right, so if we're looking for the angle that our vector makes with the positive x-axis, we want to use the x component in that formula and divide it by the magnitude of that vector. All right, so that's our first direction cosine. Then our second one will have cosine of beta, and that is the angle that our vector makes with the positive y-axis. And so that will be equal to the y component of w2 divided by the magnitude of vector w. All right, so if we want to find the angle that our vector makes with the positive y-axis, we want to take the y component of our vector and divide it by the magnitude. And then finally, our third direction cosine will be cosine of gamma, and gamma represents the angle that our vector makes with the positive z-axis. And that will be equal to the z component of our vector, w3, divided by the magnitude of that vector. All right, so if you want to find the angle that your vector makes with the positive z-axis, you want to use the z component of that vector and divide it by the magnitude of the vector. And I should clarify that this doesn't explicitly solve for the angle, it solves for cosine of each of those angles, which then you can use the inverse cosine function to solve for the angles. So let's find everything that we need here. We need to know what W1, W2, and W3 are, which isn't too hard, right? It's just the x, y, and z components, which we know are 0, 6, and -4. But I'll write them down anyway. W1 is equal to 0, W2 is equal to 6, and W3 is equal to -4. All right, but now we still need the magnitude of our vector. So let's find the magnitude of vector W. That will be equal to the square root of the sum of our components squared. So we'll have 0 squared plus 6 squared plus -4 squared, right? We took each of these components, squared them, and added them together underneath a square root. Now, if we simplify, this will be equal to the square root of 0 plus 36 plus 16, right? 0 squared is 0, 6 squared is 36, and -4 squared is positive 16. Now, 36 plus 16 is 52, so this is equal to the square root of 52, which we actually can simplify further. You don't have to do it because you're just going to be plugging that into the arc cosine function later on anyway. You'll see what I mean when we get there, but I like to simplify things as nicely as I can because you never know if it's going to make your problem easier. 52 as a factor, that's a perfect square. It's equal to 4 times 13. Right, so this is equal to the square root of 4 times 13, and we know that the square root of 4 is 2, so we could write this as 2 square roots of 13. Okay, so that's going to be our magnitude of vector W. So now we can set up each of these direction cosines. For cosine of alpha, we'll have W1 divided by the magnitude of vector W, so we'll have 0 divided by this magnitude. So I'll write that down, 0 divided by 2 square roots of 13. And that's actually just going to be equal to 0, right? 0 divided by anything is just 0, so cosine alpha is equal to 0. For cosine of beta, we'll have W2 divided by the magnitude of vector W. So we have 6 divided by 2 square roots of 13. So I'll write that down. We have 6 divided by 2 square roots of 13. And then to simplify, 6 is divisible by 2. It's equal to 3. So this is equal to 3 divided by the square root of 13. And then for cosine of gamma, that's equal to W3 divided by the magnitude of vector W. So we'll have -4 divided by this magnitude. And so this is equal to -4 divided by 2 square roots of 13. But once again, just like how 6 was divisible by 2, we can divide -4 by 2 and get -2. So this is equal to -2 divided by the square root of 13. Okay, and so now we have all three of our direction cosines. Cosine of alpha is equal to 0, cosine of beta is equal to 3 divided by the square root of 13, and cosine of gamma is equal to -2 divided by the square root of 13. All right, so those are our direction cosines, and we did want to find that for this problem, so if you want, you can box in each of those direction cosines. I didn't do that before in the previous example, but you could totally do this if you wanted to. You did need to find these for this example. But now, what we also want to find is the actual value of those angles. We need to know what each of these direction angles are equal to, alpha, beta, and gamma. All right, so in order to do that, we need to use the inverse cosine function, or the arc cosine function, on both sides of the equation. So if we do that, we'll have that alpha is equal to arc cosine of 0. We'll have that beta is equal to arc cosine of 3 divided by the square root of 13. And we'll have that gamma is equal to arc cosine of negative 2 divided by the square root of 13. All right, and then what we want to do is plug each of those inverse cosine functions into our calculator, and that will give us each of those direction angles. So if we do that, we will find that in radians, alpha will be equal to pi divided by 2. That's a pretty nice one, and you might have this memorized, but in degrees, that is the same as 90 degrees. That is an exact angle right there. That was a pretty nice one. Alpha is just equal to pi divided by 2 radians, or 90 degrees. Then for beta, beta will be equal to 0.59 radians. Not such a nice angle, but in degrees, beta would be equal to 33.7 degrees. All right, now both of those angles are rounded off. There are more decimals to both of those values. I just decided to round them off to 2 decimal places for radians and 1 decimal place for degrees. It's all a matter of preference. You don't have to do it the exact same way that I do, but that's how I decided to round off those answers. Okay, so that's angle beta. Now we have one more to do, which is angle gamma. And if you plug arc cosine of negative 2 divided by the square root of 13 into your calculator, you'll find that gamma is equal to 2.16 radians. And this is going to be a big angle in degrees. Gamma is equal to 123.7 degrees. So that is angle gamma. All right, so the angle that this vector makes with the positive x-axis is 90 degrees, or pi divided by 2 radians. The angle that this vector makes with the positive y-axis is 0.59 radians, or 33.7 degrees. And the angle that this vector makes with the positive z-axis is gamma, which is 2.16 radians, or 123.7 degrees. That describes the direction of this vector in 3 dimensions. Okay, so now we found the direction cosines and the angles for this vector. Now we have one more thing we want to do, which is to show that the sum of the squares of the direction cosines is 1. All right, we did this at the end of the previous example. This is something that we know is true for all sets of direction cosines for any vector, but we just want to show that it's true for this particular vector to finish off this example. So let's work on that next. We want to show that cosine squared alpha plus cosine squared beta plus cosine squared gamma is equal to 1. And so if we use each of these values for our direction cosines and plug them into this equation, we will have 0 squared plus 3 divided by the square root of 13 squared plus negative 2 divided by the square root of 13 squared. All right, and of course we're trying to see if that's equal to 1. Now 0 squared is 0, so we just have 0 plus these two fractions squared. We're going to square the numerator and denominator for each of them. 3 squared is 9, and the square root of 13 squared is just going to be 13. So we'll have 9 divided by 13 plus negative 2 squared, which is 4, and once again the square root of 13 squared is just 13. So we'll have 4 divided by 13, and that will be equal to 1, or at least we're hoping it is. And 0 is just going to disappear. And then we have 9 thirteenths plus 4 thirteenths. And since these fractions have a common denominator, we can add the numerators, and 9 plus 4 is 13. So we have 13 divided by 13 is equal to 1, and that, of course, is true. Anything divided by itself is 1. Okay, and so we have shown that the sum of the squares of the direction cosines is 1 for this vector, which it should be. All right, if you don't get 1 when you set up this equation, something is wrong. You either didn't square your direction cosines correctly, or you didn't add them together correctly, or you just plain out have the wrong direction cosines and you need to go back and check your work. So if you don't get 1 here, you know something is wrong. This has to be equal to 1. The sum of the squares of the direction cosines will never be another value other than 1. All right, and so that is it for this example, but I do have one more example that I want to look at before I end this video. Hey there, real quick, before we take a look at the next example, if you find my tutorial videos here at JK Math to be helpful and you want access to more content such as exclusive bonus videos and dark mode versions of my videos, I'd invite you to check out my membership site, JK Math Plus, where all of that content is available. To learn how to join and see a full list of everything you'd get access to as a member, you can head over to jkmathematics.com/plus. I'll have a link for that in the description of this video. Okay, so if you're interested in becoming a member, feel free to check that out. It's a great way to support me and the tutorials I make, as well as a great way for you to learn math better. But for now, let's get back to the video and take a look at the next example. Okay, so here's our last example. We have if the magnitude of vector v is equal to 4, the angle vector v makes with the positive x-axis is pi divided by 2, the angle vector v makes with the positive y-axis is pi divided by 4, and the angle vector v makes with the positive z-axis is pi divided by 3. Find vector v. So this is a little bit different than our two previous examples, but it still does involve the use of direction cosines. If you watched my lesson video for this topic, then you're probably aware that we can use direction cosines to create a unit vector that describes the direction of a position vector. Right? We know that one way to define a position vector, such as vector v, is to take its magnitude and multiply it by a unit vector that describes its direction. And we can express this unit vector as the following. This unit vector, for a vector in 3 dimensions, can be defined like this. We have an x component of cosine of alpha, a y component of cosine of beta, and a z component of cosine of gamma. All right, now remember, alpha is the angle that our vector makes with the positive x-axis, beta is the angle that our vector makes with the positive y-axis, and gamma is the angle that our vector makes with the positive z-axis. And in this problem, we are given all 3 of those angles. Right? We know what alpha is equal to, what beta is equal to, and what gamma is equal to. The angle that vector v makes with a positive x-axis is pi divided by 2. That's going to be angle alpha. All right? That's pi divided by 2. The angle that the vector makes with the positive y-axis is pi divided by 4. That's beta. So we have pi divided by 4. And then finally, we know that the angle that vector v makes with the positive z-axis is pi divided by 3. So that means that gamma is equal to pi divided by 3. And of course, all of these angles are in radians. All right, so we have our 3 direction angles that we can use for these direction cosines to form a unit vector that accurately describes the direction of our vector. All right, that's how we're going to find vector v for this example. We know what the magnitude is, it's given to us, it's 4, so we will have that vector v is equal to 4 times this unit vector, where we will have cosine of each of those direction angles. So we'll have cosine of alpha, which is pi divided by 2, then we will have cosine of beta, which is pi divided by 4, and then we'll have cosine of gamma, which is pi divided by 3. All right, so we just used these 3 angles that we were given in this example to set up this unit vector using direction cosines. And so if we simplify, our vector will be equal to 4 times cosine of pi divided by 2. That's equal to 0. So our x component of the unit vector is 0. Then we have cosine of pi divided by 4. That's equal to the square root of 2 divided by 2. So that's our y component. And then for the z component, we have cosine of pi divided by 3, which is equal to 1/2. Okay? So now, if we multiply 4 through this unit vector, we will have vector v. All right? So if we do that, we will have that vector v is equal to 0, 2 square roots of 2, and 2. Right? 4 times 0 is 0. 4 times the square root of 2 divided by 2 will be 2 square roots of 2, because 4 divided by 2 is 2. So we're left with 2 multiplied by the square root of 2. And then 4 times 1/2 is 2. All right, so this right here is vector v, such that its magnitude is 4. The angle it makes with the positive x-axis is pi divided by 2. That's alpha. the angle it makes with the positive y-axis is pi divided by 4, that's beta, and the angle it makes with the positive z-axis is pi divided by 3, and that is gamma. All right, vector v is the position vector of the point 0, 2 square roots of 2, 2. And so that's it. That's it for this example, and this was the last example for this video, but if you do want to see another example, I do have more available on my membership site, so feel free to look into becoming a member if that interests you. If you have any questions, feel free to leave those in the comments, but if you don't have any questions, this is all I had for now, so I will see you next time.